Good evening, ladies and gentlemen. A very warm welcome to each one of you present out here. I am Nikunj Tandon, your host for today's event, IRIS, organized by IEEE-VIT. IEEE is the world's largest technical organization dedicated in advancing technology for the benefit of humanity with over 4 million members. IEEE creates an environment where members collaborate on world-changing technologies, from computing and sustainable energy systems to aerospace, communication, robotics, healthcare, and many more. IEEE also includes a global network of IEEE members and volunteers dedicated to promoting women engineering and scientists and inspiring girls around the world to follow their academic interests in career in engineering and science. IEEE was rated one of the America's best mid-sized employers in Forbes in 2018. IEEE has been certified as the Great Place to Work. IEEE received the When Work Works Award in 2016. IEEE is a trusted voice for engineering, computing, and technology information around the globe. IEEE-VIT comes under the Bombay section. We are dedicated in conducting workshops and seminars on various domains. Adding to the accomplishment, IEEE-VIT has captured the IEEE Regional Exemplary Student Branch Award in the year 2020. We have our main flagship events, IRIS and Voyager, coming up in March. We also conduct many such great events, which includes competitions, seminars, IEEE Day, and all of these are celebrated with great enthusiasm at IEEE-VIT. A special thanks to Total Sports and Fitness, the sponsors of our event, for making this event possible. IRIS. IRIS stands for Inspire, Resonate, Integrate, and Succeed, which means to get inspired by the speaker, resonate with their thoughts, integrate them in our souls, and succeed in our lives. A series of inspirational talks resonating powerfully within the audience, integrating the advices and thoughts to walk towards success is here. IRIS 2020 was a huge success where our speakers stimulated our minds with their inspirational talks. Our speakers from IRIS 2020 included Dr. Radhakrishnan Pillai. He is a Deputy Director, Masters in Leadership Science, national best-selling author of Corporate Chanakya, and has authored 14 books. Second was Ms. Iman Jawan. She is the Director of Operations, Asia Pacific at Sanskrit, a business developer, and a forensic scientist for Mumbai Police. Third, Mr. Priyadarshan Jadhav, an actor, director, producer, and a screenwriter, a multifaceted personality in the Marathi film industry. Mr. Saurabh Bandyopadhyay, a racing driver at Volkswagen Motorsport, senior instructor at Jaguar, Art of Performing Tour, and a successful entrepreneur. They made us believe that in order to succeed, your desire for success should be greater than your fear of failure. So now it's 2021 and we are here with yet another resonating inspirational talks. Ladies and gentlemen, today we are honored to welcome one of the brightest the world has ever seen. He is here to enlighten us with his experience and knowledge so that we get inspired and be successful in our lives. Our speaker for today is an Indian physicist who is known for his integral role in India's nuclear weapon program. He played a key role in conducting the first Indian nuclear test, Smiling Buddha, or Pokhran 1, at Pokhran Test Range in the year 1974, and Operation Shakti, also known as the Pokhran 2, in the year 1998. He served as the principal scientific advisor to the federal government of India. He also served as the director of Baba Atomic Research Center, later as a chairman at Atomic Energy Commission of the Government of India, and he contributed in providing national defense and energy security to India. He was the chairman of the Board of Governors at International Atomic Energy Agency, IAEA, during the year 1994 and 1995. He's an excellent orator, brightest mind with understanding of diverse subjects, a scientific visionary of India. Our speaker for today, Dr. Rajagopala Chidambaram. Sir had been awarded Padma Shri in the year 1975 for his contribution to the success of nuclear tests. He was awarded Padma Vibhushan in the year 1999. His other prominent awards, a few of them I would like to name, are the Lifetime Contribution Award in Engineering, year 2009, the INS Homi Bhabha Lifetime Achievement Award in the Indian Nuclear Society in 2006, the Hari Om Prerit Senior Scientist Award in the year 2000, the R.D. Birla Award in the Physics Association in 1996, the C.V. Raman Birth Centenary Award in the Indian Science Congress Association in the year 1995, and many more. Sir, we are very much blessed to have you here, connected with us. Now, I would like to request Dr. Chidambaram to share his experience and inspire us. Over to you, sir.
Thank you, Kinari Bhalerao. You are Kinari Bhalerao? No. Yes, somebody else.
Sir, it's me, Nikun.
What's your good name, please?
Nikun Standen, sir.
Nikun Standen. And where is Kinari? She's around?
She's there in the meeting.
Okay, thank you. It doesn't matter. She's Miss Kinari, I think, you know?
Yes, sir.
Yes, sir. Yes, sir.
That's why when you introduced me, I got confused. Anyway, I'm very grateful to both of you for inviting me to address you young people belonging to EIT and also to IEEE. And I'll start with my PowerPoint presentation. Can we have that, please?
Yes, sir.
Are you able to see the slides, all of you? The slides are visible?
Yes, sir. Yes, sir. It's visible.
Okay, I'll go ahead with that. You know, the title of my talk is Technology is Power, because I'll explain as I go along why I chose this title. And as I said just now, it's a pleasure to be with you young guys, young people who are looking forward to build a powerful, stronger, and in every ways, one of the top countries in the world. Next slide, please. I'm very happy to learn that your institute, Vidyalankar, though it's a relatively young institute compared to other institutes of technology, has an A-grade rating from the university and then other equally high ratings from the National Board of Accreditation and then NAC. As you mentioned just now, the IRS, Inspire, Resonate, Integrate, Succeed. You know, some years back, I was talking about what I call coherent synergy. Now, you know, if you take any area in which we should work, there are universities involved, there are national labs involved, and there is industry involved, and you can also have international collaboration. And all these efforts must be synergized. And that's what people try to do when they have multi-institutional collaborations. But there must also be a coherence among the efforts. Synergy and then coherence, because there are large number of efforts. Of course, synergy itself has coherence, in the sense of physics, but I'm talking of that is local coherence. Here I'm talking of global coherence. If you want to inspire, resonate, integrate, and succeed, you young guys must have character, self-belief, optimism, and also passion. Passion to do great things for yourself and for your country. Your invitation letter said science of today is the technology of tomorrow, of course. And to this, you add the fact that technology is in the name of your institute. So I chose the title of my talk as Technology is Power. In my last slide, I'll talk about this futurologist, Alvin Toffler, who has made a very rather important statement. And I have paraphrased that statement. I'll show you it in the last slide. Into technology's power, maybe some 20 years back. That also fits in with the theme of my talk. Next slide. India for dreams. Young guys like you, but in particular, we want an India which is economically developed. The United Nations in 2015 defined some 17 sustainable development goals. Good health and well-being, and so on and so forth. Also includes climate action and all that. That is only a starting point. For us, we want to go way beyond that. We want India to become a knowledge economy. A country which has the ability to generate new knowledge and the ability to appropriate knowledge generated anywhere in the world. That's what the developed countries, already developed countries, are doing. And from the point of view of economic development, we want human development index. We are not very high on that scale. I'll define it in a moment, but we want to go well beyond that. We want to be among the top, let us say, 10 countries in the world in terms of human development index. To do this, we must have an excellent research development and innovation ecosystem. We want excellence in higher education and basic research. And we want, in basic research, I have defined something, in that paper I have mentioned. Anybody is interested, you can have a look at that. What I call directed basic research, not applied research. It's not basic research directed by anybody. It is directed by India's future needs. As I said, not applied research, still basic research, but anticipating what we will need, what will be our societal needs, what will be our industrial needs, what will be our strategic needs in the long term. We want excellence in applied research, excellence in technology development, in R&D-led innovation. And for all this has to be backed by high-quality manufacturing skills. We must generate knowledge, but we must have the ability to derive value from that knowledge. That's what innovation is about. We must be militarily strong, with the ability to fight and win conventional wars, with the ability to neutralize terrorists and low-intensity conflicts, and of course, provide nuclear deterrence. And for achieving all this at all levels, we need leaders with vision. See, our Homi Bhabha, the founder of our nuclear energy program, was such a leader. And the greatness about, there are some leaders, when they pass away, the system begins to collapse. But Bhabha created a leadership swarm around him. Homi Sitna for chemical engineering, Raja Ramanna for physics, Brahma Prakash for metallurgy, A.S. Rao for electronics, and so on. And that is why the culture he established, the Department of Atomic Energy, it has helped to nucleate so many more leaders in the next generations. There's a leading writer, a French writer called Arthur Koestler. He says among leaders there are two types. He calls them the yogi and the Kamisa. The yogi is the contemplative thinker, and the Kamisar is the man of action. Baba was a unique mixture of both. He was both a yogi and a Kamisar. He planned, showed great technology foresight, but then he was able to execute them also. Look at his technology foresight. At a time when we were not even building bicycles of indigenous design, Homi Bhabha was talking of building indigenous reactors in India. I told you about the Human Development Index. Now, Human Development Index is defined by the United Nations in terms of three parameters: the per capita gross national product. They used to use adult education, now they use literary index. At the time when I made my own definition, they were talking about adult literacy and then life expectancy at birth. 20, 30 years back, I've shown we need only two parameters: per capita electricity consumption. Because without electricity, without energy, you can do nothing. And instead of adult literacy, I preferred female literacy, because that's a measure not only of literacy, but of equity and justice in that society. And this is the curve. Each point is a country. And India is somewhere in the middle of the steep linear portion. You and I want India to go to the top, at least up to the cusp of that curve. That means our per capita energy consumption has to go up by something like 6 times before we can become a developed country in the full sense of the term. Of course, you can't become developed unless you become totally literate, 100% near literate, without gender discrimination. Now, that is why we need energy security. And this energy security today has to be achieved in the context of climate change, the concern for climate change. That's why you have to go in for energy production options which don't produce greenhouse gases, which go and settle upstairs, trap the infrared radiation from going outside. And that's why the globe begins to warm. That's the problem of global warming. Next slide. These are the low carbon energy technologies defined by the International Panel on Climate Change. This last assessment report was in 2014. The new one is coming now. Of course, during the period, they have produced a large number of reports. But in 2014, they said, warming of the climate system is unequivocal. The atmosphere and ocean have warmed something like 1 degree over the period from the Industrial Revolution to 2012. The amounts of snow and ice have diminished. Sea level has risen. That's why they say key measures to achieve mitigation goals include development of renewable energy, nuclear, carbon capture and storage, including bioenergy with carbon dioxide capture. Forestation is so important. And at that time, they had said we should limit the global warming, not more than 2 degrees. Already it's about 1 degree now, maybe a little more already. And now they are saying to be on the safe side, we should limit the global warming to 1.5 degrees. Now, a report of the International Center of Integrated Mountain Development says that more than 35% of the glaciers region could retreat by 2100, even if the global temperature rise is capped at 1.5 degrees centigrade. See the next slide, which gives a little more detail about the Hindu Kush Himalayan region. And this was prepared by the Society of Environment, Science and Environment, Center for Science and Environment, led by well-known environmentalist, Dr. Sunita Narayan. And this written by Pallavi Ghosh says, this came in May last year, Hindu Kush Himalayan region spread over 3,500 square kilometers across 8 countries, India, including India, Nepal, China, is known as the water tower of Asia. Due to its reserve of frozen water. Being a major source of water for the river, these glaciers are the lifeline for 1/3 of the population across the globe. And then she continues, glaciers are melting and receding at an alarming rate in Himalayas. Rivers, starting with the Hindu Kush region, sustain over 200 crore people. Hydropower potential 500 gigawatts. But this region is expected to lose half of its present glacier area by 2060, a decade earlier than the previously expected deadline of 2070. Now, this morning you heard the news about the breakup of the Chamoli Glacier in Uttarakhand, and that caused an avalanche, huge number of casualties, and also damage to property. The warning is coming. This warning on the glaciers, if they melt, they are going to break, avalanches are going to start, and this is something we have to worry very seriously about and make sure that we minimize global warming. In fact, you can reverse it if it is possible. Next one. That's why nuclear is so important. Of course, renewable energy is so important, and there are other sources that I mentioned. Fortunately, thanks to leaders like Homi Bhabha and the others who followed him, now India is considered a developed country in the nuclear field. The Director General of IEEE, Yokia Mano, he has said that India is remarkable many years back, about almost 8 years back, that remarkable success in the peaceful nuclear technology is an inspiration for many developing countries, and its willingness to serve as a mentor for other Asian countries that have recently joined the IAEA. Now he says India is the forefront of technological development in the nuclear sector. I'll mention to you a little bit later about our 3-stage nuclear power program, which involves fast reactors and thorium. Now, safety and reliability go together. Whether it's your personal car or some equipment at home or a nuclear reactor. If your car works reliably, very unlikely any system will fail, like the braking system or the clutch, which can lead to an accident. Now, on December 10, 2018, our indigenous reactor Kaiga 1 in Karnataka broke the world record for continuous operation of 941 days. It was been held by a UK reactor, 940. After that, of course, they have to shut down reactors for maintenance. They do it even though the reactor can run in more number of days. And this tradition continues. And Narora 2 completed 852 days before the maintenance shutdown. In these COVID days when industry has slowed down, nuclear reactors have worked wonderfully well. In fact, the third reactor at Kakarapar in Gujarat, 700 megawatt reactor, was connected to the grid on 10 January 2000, this year, last month. Next one. See, nuclear has many dimensions. Nuclear is electricity. Nuclear is also weapons. But nuclear is way beyond these, with applications, medicine, agriculture, industry, and for other societal benefits. And there have been spin-offs of the nuclear program, visible, sometimes invisible. The space program, for instance. Many of you may not know that the space program under Vikram Sarabhai was started by Bhabha as part of the nuclear energy program. In areas like high precision welding, in places like Bharat Heavy Electricals, high engineering, precision engineering, welding, these are all as a consequence of our nuclear program. In fact, there is no field, scientific, technological, or societal, which is untouched by our nuclear program. Look at the type of, this is just an example, one of my colleagues made it. We are able to export mangoes to United States, our Alfonso mangoes, because we can delay the ripening by radiation. We grow seeds by exposing them to radiation. New varieties, mutant varieties, after all kinds of clearances, after stability of the mutation. And there are dozens of varieties which are now providing nuclear security to our food security to our country. Unfortunately, somebody has cancer. What you see that the big figure is the Bavatron made by Bach. It is for cancer therapy using cobalt 60 gamma radiation. So somebody has a thyroid problem. First thing is to give him a glass of radioactive iodine, very mild dose, and then take a scan. You can find out is the potassium pickup by the thyroid is on like that and on. So in many areas of both therapeutics and diagnostics, nuclear is next one. National development and national security. You know, in a lecture in 1999, I said national development and national security are two sides of the same coin. Development without security is vulnerable. You know, Japan is so highly developed, but it is afraid of a tiny country to its northwest. Security without development is meaningless. That's why what happened in the Soviet Union, they had a lot of security, nuclear weapons, they were matching the US, but they ignored development to some extent. Now they are back on track. In the context of nuclear deterrence, in fact, in the context of even personal deterrence, we must remember that the greatest advantage of recognized strength is that you don't have to use it. That's why I tell when I'm speaking to an audience where girls are there, learn kung fu or karate, learn self-defense. An undesirable character, you can give him a karate chop at a sensitive point, he will stop bothering you. That's called retaliatory deterrence. But if the above mentioned undesirable character knows that you are capable of doing this, he will not bother you. That is preventive deterrence. That's the same principle there in nuclear deterrence. The greatest disadvantage of perceived weakness is that the enemy may get adventurous. That's why, of course, we had tested out the principle of a nuclear explosive in 1974. Physics-wise, there is no difference between a peaceful nuclear explosive and a nuclear weapon. Only the packaging is different. And of course, we knew we will have only one chance. So we tested all the 5 types of devices we wanted. The fission device, which actually had been made 15 years earlier, we checked it out. Thermonuclear device with an advanced fission booster, fission trigger. Then what I call the 3 chotus to prove physics principles. Less than 1 kiloton. We call them 0.2 to 0.5 sub 0.5 kiloton, sub kiloton. So all these proved all the things we wanted: explosive ballistics, shockwave physics, neutron kinetics, physics related to the radiation coupling of the 2 stages of the thermonuclear device, and how to estimate precisely the yields, and so on. Everything we tested it out, and the radiochemistry. You know, after the device is tested, few months after things have cooled down, you can go and pick up the rock from near the shot point, and you can do the radiochemistry and accurately estimate the yield. And everything was perfectly as per prediction. Next slide. See, that's why, no, of course, we had a collaboration DRDO on the explosive ballistic side when we had to design the explosive lenses, mainly the Terminal Ballistics Research Lab. And of course, the people who did it first, the Manhattan Project, the Americans, of course, they didn't have at that time the kind of knowledge of physics that we have today and the kind of computing power that we have today. But today we have the capability to design and build. We are already building, of course. We have a stockpile. Nuclear weapons from low yields up to around 200 kilotons. After the tests, of course, a great deal of further scientific work and technical development work has taken place. I'm now going to show you a cartoon. No, not this, not after this. No, go back. Go next slide. See, this was no. Go to the Venn diagram. This is the Venn diagram published by a couple of Americans after our nuclear test in 1998. And if you guys remember your Venn diagram, set theory, each circle represents a country. When two countries' circles overlap, knowledge has been transferred from that country to the other country. UK and US, of course, worked very closely together during the early days that continued. UK to France, US to France, France to Israel, Israel to South Africa. Transfer of knowledge about nuclear weapons. Russia to China, China to Pakistan. And as you can say, my good old India stands alone. What they are saying is, India did not get any help from anybody, nor did they spy and seek knowledge from anybody, because we were confident that we can develop all the knowledge needed in our own country. Next slide. I'm going to show you a cartoon. This is a funny cartoon preceding our test. There is a suited guy who's taking, obviously, a Vasana, telling an Indian guy who must be a MP or a minister with a Gandhi cap, and he tells him, "You must not make the bomb. Why do you want the bomb?" And the white, "If I had one, you wouldn't talk to me like this." Next one. See what I said, our interest is in nuclear power. And this is a document from the World Economic Forum, which meets in Davos every year, December. This is from December 2019. And in fact, nuclear power is one of the areas there. And what they are saying is electricity demand is increasing about twice as fast as overall energy use, and is likely to rise by more than half by 2040. Because as you know, electricity is the most convenient form of energy. Nuclear power, 10% of the world's electricity, and in the OECD countries, European OECD, Europe, 18%. At the moment, there are 450 operating nuclear power reactors generating about 400 gigawatt. 1 gigawatt is 1,000 megawatt, as many of you may know. Almost all reports on future energy supply from major organizations suggest an increasing role for nuclear power as an environmentally benign way of producing reliable electricity on a large scale. And this report, as you can see last year from the World Nuclear Association, about 30 countries, including many developing countries like Bangladesh, are considering planning or starting nuclear power program. Next one. This is our indigenous three-stage program from the time of Bhabha. First stage, pressurized heavy water reactors. We had Canadian collaboration when we built our first 220 megawatt reactors. Then we indigenized it. Then on our own, we designed the 540 and 700 megawatt pressurized heavy water reactors. And the one I showed you in Kakrapar 3, that is our own design 700 megawatt reactor. The plutonium from these reactors goes into the second stage, and that reactor is a fast reactor, fast in the sense it uses fast neutrons rather than thermal neutrons, can produce electricity, but it is also helpful in converting the large reserves of thorium-232 that we have to uranium-233. And in the third stage, that will come much later, we will go into the thorium-232, uranium-233 cycle. This is our program, which is what Yuki Amano was referring to. But we will import and develop indigenously also with the international collaboration, the light water reactors, the reactors in Kalpakkam, Kudankulam, the 1000 megawatt Russian reactors. They are working very well, and we are going in for more reactors. And if the techno-economic viability of other agreements we have with the US and France works out, then of course we can build their reactors also. And the ultimate stage will be our own indigenous light water reactor. This is what we call the closed nuclear fuel cycle. In the nuclear operation, we start with mining, milling, then fuel fabrication. You design the reactor, build it, take out the fuel, reprocess to take out the plutonium, put it back into new kinds of reactors. Whatever is left over is radioactive waste, and then you have interim waste storage, and then you have final storage. This is all the operations in a nuclear fuel cycle. Closed cycle will be you don't reprocess, you just throw away the spent fuel as waste, which is, as I told you, is not economic. If you have a given amount of uranium, I'm talking from the point of view of the world, not just India. If you reprocess and close the fuel cycle, that means put it back into new kinds of reactors, like we are building in Kalpakkam. Same uranium will give you 50 times more power. If you include thorium in your closed fuel cycle, the same uranium will give you 600 times more power. That's the advantage of closing the nuclear fuel cycle. And the whole world has to come to this. And fortunately, thanks to the visionary leaders we have had, we have a lead in this. See, there is a very interesting author called Nicholas Taleb. I don't know, some of you might have read his book, The Black Swan. He wrote another one, Antifragile. And he said, fragile are things which break under stress. Robust are things which resist stress. So he defines a new kind of system, anti-fragile, which gets better and better under stress. Of course, unfortunately, there are some microbes which get better and better under antibiotics. They become resistant to that. But what I have said here is this is also true of a nuclear program. There were technology denial programs to stop and slow down our nuclear program, but it had the opposite effect. It had given us, as I say, immunity against technology denial. Because we all talk of Atmanirbharta today, self-reliance, which is very important for India. And I had defined when I was director back, how many years? 30 years back. I defined self-reliance as immunity against technology denial. You're building a complex system, and if something is denied, something is available to you, which you want to put in your system, available from a reliable source. Don't waste time building it. Build the main system and take the subsystem. That's what every country does. But if anything is denied to you, including the proverbial wheel, you must have the ability to do it yourself. And the stronger you become, the denial will slow down. That's what happened. Nuclear supplier group guidelines have now been relaxed for India. And of course, we should leverage international cooperation. Initiatives should be ours, but to strengthen them, that's what every country does. They use it, leverage our cooperation also. We must go for scientific cooperation, whether it is in basic research or in technology development. You might have heard some time back, the discovery, it got strangely called the God particle. If anybody is interested in your questions later, I'll answer it. But actually, you're looking for the Higgs boson. Higgs boson was the only missing particle in the standard model of the nucleus. If you believe in the Big Bang theory, when the particles were all produced, the masses to them were given by the Higgs field through the mechanism of the Higgs boson. And Higgs boson, that was one particle which they had never seen. And do you know why it's called a boson? There are only two kinds of fundamental particles, the fermions and the bosons. Fermion is named after Enrico Fermi. Any particle of spin half is called a fermion. Electron, spin half. Any particle which is zero or integral spin is called a boson, like your photon. Light particles are quantized. That's a boson. So the Higgs boson, see, when two particles collide, energy disappears. Two particles collide. And the higher the energy of the colliding particles, the higher is the mass of the new particle produced. And they knew from theory that the Higgs boson was something like 130 to 150 times the mass of the proton. You know, E is equal to mc squared, Einstein equation. Many of you, have, at least those who have studied physics, would have known E is equal to mc squared. When mass disappears, you get energy. That's how you get nuclear energy. Mass disappears when you fission uranium or you fuse isotopes of hydrogen. But here, when energy disappears, mass is produced. The higher the energy which disappears, the higher the mass of the particles that you produce. And to get the Higgs boson, they had to collide particles at several tera electron volt. You have 1,000,000 electron volt, 1,000 of that is giga electron volt, 1,000 of that is tera electron volt. And that's what they did in the Large Hadron Collider. Some of you may know that 100 meters below the ground in Geneva, there is a 26-kilometer tunnel in which, in a ring, protons are moving in opposite directions. Protons are a kind of hadrons. Once in a while, they are brought together. And when they collide, the energy disappears. The protons are bent by dipole magnets, with charged particles. They are focused by corrector magnets, sextupole, decapole, octupole magnets. All these 1,800 magnets, superconducting corrector magnets in that 26-kilometer circumference ring, worth $40 million at European cost, was supplied by the Department of Atomic Energy. That's what you see over here. And of course, we are also collaborating in thermofusion energy. The best design so far, magnetic confinement fusion, Russian design, tokamak as it is called. Next slide. And this is the ITER program, International Thermonuclear Experimental Reactor. And there are 7 or 8 major countries which are collaborating. India is one of them. And we are providing equipment, not cash so much, but equipment for that. See, this tokamak, which is a donut kind of thing, is located because that has to be at very low temperature. Plasma is at a very high temperature. Plasma is 510 million degrees, 50, 100 million degrees. And there is no material which can contain it. It has to be confined by a magnetic field, so it's called magnetic confinement fusion. But that tokamak has to go inside a cryostat. And this cryostat is the world's largest cryostat, 30 meters in diameter and 30 meters in height. This was supplied by India. This is being supplied by India, built by Larsen and Toubro under the direction of Institute of Plasma Research. And the base of this ITER has been actually installed at Cadarache in France in 1920. The fusion science, fusion is what I said when I inaugurated the conference last year back in Gandhinagar. Fusion science is a physicist's delight, but the technology is very complicated. So I said fusion technology is a nightmare for engineers. Next one. Of course, there are other departments. Wonderful. We are very proud of our space programs, satellite launch vehicles, 100 satellites they launch, Cartosat mapping satellite. ISRO launches satellites not only for India but for 20 other countries. And also they have launched nano satellites for student-made nano satellite. They're planning for this Gaganyaan. Chandrayaan 2, which was a spectacular project. Of course, the rover failed, but the other thing which is circling around is giving enormous amount of information. I would consider 95% successful. The lunar orbiter is in perfect condition, sending data about the minerals which are there in the moon. Next slide. The department at DRDO, this is another very important department, developing very good. Not one technology, all these technologies have, and this Tejas aircraft is a very good fighter aircraft, and they have been, it's a flagship program for the Make in India program of plan of the government, and they have already been introduced in the Indian Air Force. Research, development, delivery. Research, development, delivery. This is the chain. I mean, this was taking for a lecture from Kenan Sahin of MIT. Research, developing knowledge. Developing it to a form which can be delivered to the user. Delivery. In the case of industrial development, academic institutions are very good in research. Industry is very good in delivery. Both are poor in development. And that's why when I was the principal scientific advisor, I created these interfaces for various sectors. Industry, academia, industry interfaces. In the case of rural development, knowledge is there, delivery is the problem. The knowledge transfer. Or you can do other kinds of innovation. Next slide. As I said, one of the areas we took up for in this academia industry interface was machine tools, because most of the machine tools in India are imported. And we had funded a project from PSA's office in IIT Madras. And they have made the world's best grinding machine tool that you see over here under the guidance of Professor Ramesh Babu in IIT Madras. And this project has been so successful that the Department of Heavy Industry, the Government of India, has started a Center for Advanced Manufacturing under Professor Ramesh Babu and has given him a large sum of money to take up something like a dozen projects, which are all going very well. I visited this Center for Advanced Manufacturing in IIT Madras. Next one. This is rural development. I started this in 2004 because India is a very big country, and our needs, technology needs, range from nuclear and space to rural, and it has to be demand driven. RUTAG, which I started, is actually an open platform, demand driven innovation strategy. And it is centered in 7 IITs, but of course we link with other institutions and through the IITs to many other organizations. Next one. See, for example, just now there has been this flooding in Uttarakhand. 5 years back there was also flooding. A lot of bridges, lot of ravines were flooded. And this is a natural ravine. Like that there are hundreds in Uttarakhand. This is in a village called Bagi. And the villagers live on one side of this ravine. Their kheti, agriculture, is on the other side. And then normally the load is brought by women, and they go through this ravine, go down and go up. And the water, there can be various levels of water over here. When you put your foot on the rock, you don't know where you are putting it. And the least that can happen to you, you can sprain your ankle. And at that time, 5 years back, a couple of young women had been washed away in these flash floods, like the one that is happening today in Uttarakhand because of the Chamoli Glacier break. And at that time, Dr. Anil Joshi, who runs an HESCO organization, and Himalayan Environmental Service, said we will build small bridges. I used a technique which the Harvard guys call knowledge brokering. See, what they say is that most innovations are old innovations packaged for a new environment. You talk about the steamboat, but the steam engine was used in mines for 75 years before that. So I happened to visiting a lab, DRDO lab in Pune. They were building bridges for our army. So I said, why? Don't have to be a boat. And now it's our project, and to also other places in Rajagopala. See, you read what I have quoted from Homo Deus, this book by Yuval Noah Harari. He wrote his first bestseller, Homo sapiens. Humans nowadays completely dominate the planet. Not because the individual human is far smarter and more nimble-fingered than the individual chimp or wolf, but because Homo sapiens is the only species on Earth capable of cooperating flexibly in large numbers. And communication is the foundation on which this cooperation is based. And communication is a part of that. It's also a part of your IEEE important subjects. So when I was the PSA, we initiated this project. This Indian National Knowledge Network is built by the Ministry of MIT, National Informatics Center. Director is R.S. Mani. You guys it would be nice if you call R.S. Mani to give you a talk about the network. You see, the phase one, we connected only the government institutions, all national labs, all national state universities are connected. But in phase two, they would be connecting the private universities also. So if you contact them, you get in, and you may have to pay a little bit of money to pay for the optical fiber from the node to your institution. But this is the world's largest research and education network connected to the sun grid. I told you about our TFR guys, they did the experiment, which gave the indication of the Higgs Boson. That data comes live to them because the sun grid is connected to the NKN. So it is connected to the European grid, it's connected to the internet too. And this is a very reliable, because what it is, there is a backbone network. The supernodes there, any two of them are connected by at least two network service providers, different network service providers. So even if one fails, the other one takes over. And from each one of them, this is scalable. It started with 10 gigabits per second, now it's 40, and from each one of those supernodes, the 1,600 institutions are now connected. Each starting with 1 gig, and it's going up. Next one, please. Then, of course, there are other areas you should be interested in. This Nano Electronics programs. This also started from the PSI's office when I was there. And we funded this project through the MIT. 2 Nano Electronics world-class facilities in Bangalore, Indian Institute of Science Bangalore, and IIT Bombay. And there is a national users program, and already 500 projects for 300 institutions are there. international collaborations. And you young guys from VIT, you can go and use it if you like. You can contact them. And there are so many colleges, universities. Maybe you are already doing it, I do not know. And you can certainly use the one. And there is this iSTEM program also created by our office. You see, the government wanted, the new government in 2018, just before 2018, that all science in equipment bought through public funding should be available to everybody in India. So we created a network which is centered in this Center of Nanoscience and Engineering, Institute of Science, Bangalore. It's called iSTEM, Indian Science Engineering Facilities Map. And you can open, if you can open this website, iSTEM's website, all those who have kind of registered into this, who are willing to make their facilities available. And you can pick up the nearest facility that you need and can use it. Next one. See, there are a lot of other areas which really are part of your interest. Cyber security is very interesting. Leon Panetta, even in 2012, US Defense Secretary, predicted the cyber Pearl Harbor. The next Pearl Harbor for the United States will be cyber based. See, this is the interesting thing. The more you connect, the more convenient it is. But the greatest security is in isolation. Of course, you can't isolate yourself. Your firewalls, intrusion detection, prevention systems, antivirus software, other security tools. But hackers and intruders and attacks are continuously getting smarter. And as the McAfee Labs report says, they are also learning to leverage artificial intelligence and machine learning. Next slide. Quantum computing, getting hotter. Of course not. It may take 10 years and more before it becomes practical. And quantum communication, quantum computing, quantum cryptology. A lot of players in this. Google, they claim they have built the world's fastest. The IBM says your algorithm is not perfect. But there are many other players. India also, there are people who are working on this area of quantum computing. In classical computing, you use it 2 bits. 2 bits, 0 and 1. Quantum computing, you can use any number of bits. In the case of Sycamore of Google, 53 qubits. So they carried just this fairly related simple problem, random number generator, using some algorithm. And they claimed it will take 10,000 years for the classical supercomputer to complete this job. But IBM said I can do it in 2.5 days using a different algorithm. But still, many people are on this job. And the fear also in quantum cryptography is any classical RSA code can be broken by a quantum computer. And if a quantum computer creates a code, no classical computer can break it. So it's one area in which we have to be up to date. Of course, artificial intelligence, all over the place. There is no field in which from the absent. Because we have humanoids, they look like humans, humanoid robots. And actually this lady, Sophia, she has become a Saudi Arabian citizen. And people are scared of this. That's what Masahiro Mori says. If you make a robot, the people are very excited. But if you make it look too much like a human, because this lady was asked, I think it was one of the ones, this Erika, no, I think Sophia was asked by a smart correspondents. And said, you talk like a human and you are able to answer everything. But what is it that makes you a robot? And she asked the interviewer, you tell me, What is it that makes you a human? And the interviewer could not answer. Next. For the future, some people are scared. I'm not scared of artificial intelligence. I believe with Roger Penrose that if you apply this Gödel's incompleteness theorems in mathematics, we come to the conclusion humans will always be smarter than computers and computer algorithms and any other cybernetic machines that they create. And I completely agree with next one. And you see, there was this wonderful book on Srinivas Ramanujan, the mathematical genius, and the man who knew infinity. And this was reviewed by this guy from Yehezel, the Hebrew University of Jerusalem, and he says that Srinivas Ramanujan, you cannot compare him to a super intelligent robot. He says he was a man, even today, whose theorems would at intellectually back-breaking cost. Nothing in the Ramanujan notebooks have been proved wrong. He liked the Shrutis, that he wrote the theorems without proof. And people are still trying to prove his theorems. And he says, and this man says, no enhancement of human intelligence through these algorithms can open a door to becoming a Ramanujan. Next one. If we come to my last slide, this is what I said. Technology is power. I paraphrased it. This is Alvin Toffler's famous statement, where he said, yesterday violence was power. Because he wrote it some time back. Today wealth is power and tomorrow knowledge will be power. And yeah, why did he say this? Yesterday violence was power. Whoever has the best technology for violence is the most powerful. Still true. Wealth is power. Whoever has the best lot of money to convert knowledge into technology is the most powerful. And of course, knowledge will be power. Knowledge is useless unless it is converted into technology. Of course, basic knowledge must be acquired for its own sake, as Swami Vivekananda said. I'm talking about utility. Now, what is common in all this? Best technology for creating violence. Best technology to be created by wealth. Best technology to be created through knowledge. So I paraphrase Alvin Toffler to say technology, power is likely to be so in the foreseeable future. Because it is so, countries and companies try to dominate technology, whether it is nanotechnology or nuclear weapon technology. They use two mechanisms, intellectual property rights and technology control regimes. If you want India to be a global technology leader, India should be in the forefront in creating IPRs and make itself immune to technology control regimes. And India should have the ambition to be the first introducer of new advanced technologies. Some people say, let us wait, let somebody else prove it. We'll use only proven technology. And I tell them, proven technologies are a synonym for obsolete technology. So you young guys from VIT, you all want India to be a global technology leader, to take the lead in creating intellectual property rights, to continue to keep India immune to technology control regimes as we have done in nuclear and space. And you take the risk to be the first introducer of new advanced technology. You don't want to be the first. You will always be the follower. You will never be the leader. Certainly, you young guys don't want to follow others. You want India the leader and you want to provide leadership. Let me stop with that thought. Thank you. No, close it, close it. I don't want all. Close it.
Thank you very much, Chidambaram sir, for a spectacular presentation. Your philosophy on the concept of leadership and how it can change today's world, especially in the field of technology, the future of nuclear energy, and the need of self-defense. The Venn diagram, which indeed says that our indigenous nuclear program helped us not only depend on any other country, but also to build self-reliant or Atmanirbhar technologies for India. India surely has the ability to fight back, and we will grow stronger and stronger. Thank you, sir, for your remarkable contribution in India's nuclear weapon program. Thank you, sir, for showing us the science behind nuclear fuel cycle. And rightly said, the best innovators use old ideas as the raw materials for one new ideas after another. Thank you, sir, for briefing us about the Nano Electronics program and quantum computers. Technology is indeed power, sir. I would like the audience to ask questions in the chat box. I'll convey it to sir. So, having worked closely with ex-president Dr. APJ Abdul Kalam, can you share some experience working with him?
No, actually, very interestingly, when in 1970, before you were born, of course, before you were born, before your mother was born. When was your mother born? After
She was
1970.
born in 1977, sir.
See, before your mother was born,
Yes,
I
sir.
met Vikram Sarabhai. At that time, I was designing the explosive device for the PNE experiment. And at that time, the chairman was Vikram Sarabhai. And I was telling him, you have to create a spherical shock wave. So I'm going to have to surround that material, nuclear material, with a number of explosive lenses. All of them have to be detonated simultaneously. So I'm looking for detonators which are high-speed detonators. So he told me that I have a young man in our now it is called Vikram Sarabhai Space Center, which was the space center in Trivandrum. And I'm going there for their annual meeting, that board meeting, where Sarabhai used to chair that the space center. You come along with me next time I go. I will introduce you to this young man. And that young man turned out to be Kalam, So I met him. But in the event, of course, the separation of stages in the space vehicle, that detonator is 1,000 times slower than what I wanted. More than 1,000 times. I got it from DRDL eventually. So that is the first time I had an occasion to meet him. Then I had really not much contact with him, because between 74 and 98, BRC was designing the nuclear weapons. The main DRDO lab was the Terminal Ballistics Research Lab in Chandigarh, with whom we were collaborating. Then, when I was chairman Atomic Energy Commission, he became scientific advisor to Raksha Mantri, or the chairman of that Defense Research and Development Organization. And we had a large number of contacts. I have traveled together with him, and we have traveled to Russia, and he told me a story, I told him a story, but he had no time to hear stories. Any questions may be there. So that is how, and then of course, during the management of the test, we worked very closely together. And Pokhran was managed, usually managed by you must separate the design part, which I have been doing from, I told you, before your mother was on to this time. But management of the test is done by the chairman of the Atomic Energy, like in the old days, Ramanna and Nag Chowdhury, in the old days. Then that is when we worked very closely together and with the government of Vajpayee's government too.
Okay, sir. So there's this question asked by Karzan Kumana. So what motivated you to take up a research field in physics?
So you see, the thing is, I loved physics. So, you know, sometimes in your career, it will happen to all of you, I tell you. Sometimes there are perturbations. No? See, I passed out physics honors, PhD physics honors from Madras University. In fact, I was first ranker in that university. So, but then at that time, the steel plants were coming up. And just as I was talking about technology's power, at that time I thought, if you want to go from an agricultural economy to a industrial economy, metallurgy is the answer. We have to make steel plants and other plants. So I applied for admission to the Indian Institute of Science, Bangalore, in the metallurgy department. And it so happened, accident, I was staying with one of my relatives who was a professor of foundry engineering in the Institute of Science, Bangalore. And we were going for a morning walk. And we met Professor R.S. Krishnan, who was the head of the Department of Physics in the Institute of Science. So my relative, Professor Ramurthy, introduced me to him. So this is Chidambaram, first ranker from physics honors. He is now changing to metallurgy. Krishna, no, he's not changing to metallurgy. He's joining Department of Physics. Now that was that. So purely by accident, I remained in physics. Then of course I have not deviated. I didn't have any ambition. Most of my colleagues after PhD wanted to go abroad for a postdoc. I was not interested. Then coincidentally, there was an invitation from Dr. Rajagopala to come and join. At that time, I was working on hydrogen bonds, not bombs. Hydrogen bonding is the most important, very important interaction in biological molecules using the technique of nuclear magnetic resonance. Because I was studying smaller things like hydrates, and better than nuclear magnetic resonance, the neutron scattering. I'm through after boring you with my no.
No, sir. I guess there was a network issue.
Network problem. Okay.
Yes, sir. So Kinnari asked that what best sums up your vision for the country in terms of advancement in technology?
See, this is what you need, what is called technology foresight. Technology foresight. Now, technology foresight is different from technology forecasting. You can take up any technology. You can say, you can predict, is it likely to succeed or not? But if you add to it assessments based on your country's needs, on your country's resources, that becomes technology foresight. Technology forecasting plus assessment based on your country's requirements, it becomes technology foresight. On that basis, you can decide what are the critical technologies for India. But then, the problem, India is not Rwanda. You know, I was in a science advisors meeting in New Zealand.
Yes.
And there was this gentleman from Rwanda who was a science advisor. And he said you can talk on biotechnology, nanotechnology, information technology, but I told my president that the most important technology for Rwanda is how to clean coffee beans, because it's a single product economy entirely based on coffee beans. But India is a huge country. So in that sense, you have to convolute what I said with the size of the country and the diversity of the country, but still some things remain. Nuclear, space, defense related, and every one of the other areas which you mentioned, whether it is nanotechnology or biotechnology or artificial intelligence, or you factor in what are your requirements. Machine learning, artificial intelligence, big data analytics. At what time do you want to get into quantum computing? What areas of cyber security that you want to work on? All these become very, very, very important. Nanotechnology. Which areas of nanotechnology? Because nanotechnology can be in any field. It's only a broad starter. So one has to look really, but then it has to be convoluted with the abilities which the country's scientists and technologies have. Factor that in. Then from there you branch out. That is why you must have technology continuity. Technology, if there is a break, and you see, when you have a professor, let us say you have a professor, or you are working in a national lab, you know, the professor knows many more things than what he has taught you. You must always have an understudy. A man building a nuclear reactor or any part of a nuclear reactor must have an understudy who learns not only from equipment, not only from documents, but from things this man has not put down on paper. Imagine a situation in which this man retires and that knowledge has not been transferred. That knowledge is gone forever. That's what I tell my American friends. You are having a discontinuity in nuclear technology. Not India, not China also. And one day you are going to come to nuclear power. If you are serious about climate change, once you shut down your fossil fuel plants and you start getting more and more of this glaciers like the Chamoli glacier which came this morning, the world will get more and more serious about global warming. And then you will have to go to nuclear. But by that time, since you have not built nuclear power plants, your knowledge would have dissipated. But we are ready to help you at that time. We want you in the short term. You will need us in the long term. You have to factor in this also. For India, you have to go in area by area and decide. Whether it's agriculture, there are technologies there. Agricultural technologies, water technologies, desalination technologies, water purification technology, any area you tell me. And then you decide what kind of technology you will need. And everywhere there are openings. Actually, there is, suppose I look back and say, there is no technology from which India can afford to be absent. But no technology is a single technology. You have to decide.
Yes, sir.
Develop your interest, and everywhere you will find a niche. Your interest and India's needs must. There is a famous biologist. He wrote a very nice book called Advice, Nobel Prize winning in technology. Advice to a young scientist. Advice to a young scientist. And this advice to all of you guys, also to old scientists, always work on important problems. Important to science or important to society. Everything is here. Always work on important problems, important to science or important to society. Well, how do you know it is important? That's no problem. You have to study, and there are plenty of sources of information apart from your professor. Professor Google is there, but you must do in a focused way and make sure of the reliability of the source by going to the original paper. Very often the summaries are written by high school dropouts in order to earn money. Be careful. I'm through. Go ahead.
Yes, sir. So there are a lot of questions asked in the chat box. So what I'll do is I'll pass out a Google form to everyone. They'll ask their question. So my last question to you is, so how was your experience at Pokhran?
Cool.
Can you share your experience, sir?
You know, 74, of course, was the first time we went there. We were delighted. First time we were doing it there, and we are the only country who did their first test underground.
Yes, sir.
And it was successful. You know, when you, I will not go too much on the phenomenology of underground nuclear explosions, but whatever it is, when you do something underground, you get the yield what you are looking for. Apart from the vaporization, the melting, cracks go from the short point towards the ground surface. And when the shock wave comes and hits the free ground surface, what comes as a compression wave lifts the ground, and that ground falls down. There cracks go from there to here. And the two must not meet, otherwise there was venting of radioactivity. And we had made careful calculations in all the tests, both 74 and here, that if you go too deep, you are wasting energy. If you put too shallow, you are venting radioactivity. Go below the optimum depth, make sure no venting. And this we succeeded. So that was apart from getting the exact yield, that we didn't release any radioactivity. We stood on the ground both 74 and 98 a couple of hours after the event, and we brought Prime Minister to stand there 2 days after the event. So that was another one. Mainly that all our physics calculations were perfect, and then we could build on that. And of course, it's not one; it's a huge team here who did conducting the experiment, connecting the wires, making sure the signal goes, all the safety things are taken care of. The signals are recorded in our seismic station, close-in accelerators, all those, that's all. And the radio chemists and the people who prepared the materials. It was a huge team effort. Everybody was happy. Somebody asked Ramanna at 1974, did anybody get hurt during the 74 explosion? He said yes, one crow. Poor thing was sitting on the place above the event. It got hit by that. See, that was the only injury.
Yes, sir. Thank you so much, sir, for connecting with us. It was really inspiring. Sir, now I would like to call upon the chairperson of IEEE-VIT, Mr. Aryaman Rao, for a vote of thanks.
Thank you, Nikunj. Sir, it is my great privilege that I have this chance to present the vote of thanks today. Dear Mr. Chidambaram, it has been an immense honor to have you with us. Your contributions to science and our great nation is something every Indian will forever cherish with pride. On behalf of our entire college, committee, and all our students today, I would like to thank you for your illuminating discussion and for introducing our students to such a unique perspective on India and technology as such. Thank you for joining us today.
Thank
I would
you.
further extend my gratitude to our convener, Mrs. Ulka Padwalkar, and all our teaching faculties for giving us this opportunity and motivating us to strive for success. An event like this cannot happen overnight. Weeks of preparations and hard work have gone into setting this up, and we are very lucky to have a team of dedicated student volunteers who toiled to make this happen today. Thank you to the entire team. Moving on, we would like to specifically thank our sponsors, Total Fitness and Sports, for supporting IRIS. I would request everyone to check out their store for all athletics and sport related needs. Last but not least, we are grateful to the entire audience who has shown up today in such an amazing number for sharing their valuable time with us. I hope everyone has enjoyed today's seminar and has imbibed something important from it along the way. Thank you all, and I hope to see you again next weekend with our next set of speakers. One request to the audience, please remember to fill the feedback forms as we enable us to keep providing you all with quality events like these. And thus, I would like to end the vote of thanks from my end. Thank you. Thank you so much.
Thank you, sir. I'll take leave of you now. Thank you.